Yeah, very good morning. Today we are going to see a very important topic of the model evaluation matrix. So, why do we spend time on this? So, first of all, I am Karthik N, working in the Department of Mechatronics at SNS College of Technology. So, why do we spend more time on this model evaluation matrix? Because building a model is only half the job. Knowing whether it is actually good, reliable, or useful in production is what separates the academic exercise from real industrial systems. So we'll cover classification, regression, cross-validation, bias variance, and finish with a quick recap. So first, why does evaluation matter at all? So we evaluate models to validate how well they perform on unseen data. First one is quantify prediction accuracy or error, discovering the weakness. Maybe it fails badly on rare events, and make sure the model actually meets business and automation goals, like minimizing the downtime cost, not high, just high accuracy. So this will show in the good evaluation, better model selection, better decision, the predictive maintenance, quality inspection, energy forecasting, and etc. So we group metrics according to the task, that is the classification, predicting discrete labels, that is good or bad part, fault or no fault part, pass or fail part, followed by the regression, predicting the continuous values like temperature, pressure, remaining useful life, energy consumption, and the last one is the clustering, group of similar items, that is anomaly grouping, pot family preparation, pot family formation. So today we focus mainly on supervised learning, that is classification and regression. These are the most common in the automation field. So let's start with the classification. The foundation is the confusion matrix. So it is simply a 2 cross 2 table of prediction for binary problems. So we can extend it to multi-class. That is, row is equal to actual sums and columns is considered as a predicted class. So for cells, that is TP, true positive, correctly predicted positive got the defect, and a TN, truly negative, correctly predicted negative, FP, false positive, wrongly predicted positive, that is false alarm, costly maintenance, and FN, false negative, missed a positive, dangerous defect positive. So look at this diagram. Imagine pointing to confusion matrix visual, that is example image 0 or image 1. Very clean layout. Many students remember it better once they see it colored this way. So from the confusion matrix, we derive the most used matrices like accuracy, that is TP plus TN divided by total. This is simple but misleading when classes are imbalanced. For example, 90% 90% of good parts, followed by the precision, which is equal to TP divided by TP plus FP. Of all predicted positive values, how many are actually positive? So very important when false positive are expensive. For example, unnecessary machine stop. Followed by the recall, which is more sensitive, that is TP divided by TP plus FN. Of all actual positives, how many did we catch? So critical when missing positive is dangerous. Missed crack in the component. And the F1 score is equal to the harmonic mean of precision and recall. So single number when you care about both equally. Then we have the ROC curve and AUC. The ROC plots true positive rate or recall versus the false positive rate at different threshold. That is the point to ROC example. Image 3 or image 4. So AUC is equal to area under curve, which is almost to 0.5 means of random guessing, and 1 point and actual value is 1 means perfect model. When AUC is greater than 0.8 to 0.9 is usually strong in the industrial applications. So here comes the regression part. So we predict the numbers. So we measure how far off the predictions are. The main ones is the MSE, that is mean squared error, average of squared differences, to the penalizes large error heavily. And the RMSE square root of MSE, same unit as target, example degree Celsius, bar and kilowatt, easier to interpret. And MA is mean absolute error, that is average absolute difference. Treat all error equally. The R square is the coefficient of determination. How much variance in Y is explained by the model. So R squared is equal to 1, which is a perfect fit, and R squared is equal to 0, as good as mean. When it goes negative, worse than mean. So look at the scatter plot versus the actual plot. We can able to detect the point closest to the 45-degree line is equal to good model. The vertical distance or the errors we measure. So never trust the performance on a single train test split. It can be lucky or unlucky. So we use cross validation technique to get more robust estimate. Most common is the k-fold CV. Split data into k parts, usually 5 or 10. Train on k1, test on 1, rotate average result. So stratified k-fold, especially for classification, keeps class proportion in each fold. So leave one out. Extreme case, k is equal to n sample, very reliable but computationally heavy. So this greatly reduces the risk of overfitting to one particular test set. One of the most important concept in the modeling is the bias variance trade-off. Hide the bias, it's underfitting. Model is too simple, misses the pattern, it leads to the poor on train and test. And overfitting, model is too complex, memorize the noise, excellent on train, poor on test. So we want this sweet spot is good generalization. Look at this classic plot. As model complexity increases, bias decreases, but variance increases. So total error has a minimum. What is our goal is to find the complexity that minimizes the test by the generational error. So here's a nice summary and mind map. So the classification followed by the accuracy, which gives the precision and the recall, then F1, then ROC to AUC regression, and followed by the mean square error, MSC, RMSC, MAE, R square plus cross validation methods, and bias variance at the center. So everything connects to a common concept called the evaluation matrix. So here comes the quick recap. Start with the confusion matrix, precision, recall, regression modeling, and always use the cross validation, k-fold stratified most practical. Understand the bias variance, avoid both under and overfitting. So proper evaluation is what makes models trustworthy in automation. So predictive maintenance alerts you actually act on quality prediction you trust, etc. Next class, we will look at the same, some real Python example calculating these matrices. Thank you. You can see in the next class.